To compute integrals of rational functions in general, it turns out that basically we've done all the relevant computations of integrals already, because we can basically trace everything back to the cases we've studied before and kind of using a smart way of kind of how to reducing this to the situation. And this smart way of reducing it is the so-called partial fraction decomposition. And this I need to prepare with some elementary theorems about polynomials, which are really not that complicated, and you can also really do this by elementary methods. So with our knowledge it will be no problem, but I will leave out the proofs just because I don't have the time for this. First thing is theorem 536, the so-called factor decomposition theorem of polynomials. And I consider the real case. You could also do this for complex polynomials, then it gets a bit simpler, of real polynomials. So I'm still considering f of x equal to p of x over q of x, now again back in the general case. The factor decomposition now says that if q is an arbitrary real polynomial, so assume that the degree of q is n, then you can show that there exists some number k between 1 and n, and real polynomials q1 to qk such that, first of all, they're related to q as follows. We just demand that q of x is the product of all these polynomials. So q1 of x times q2 of x times to qk of x for all x in R. Okay, and the interesting thing, the special thing is now, we can always find such a decomposition by factors. I mean, of course, so far it's trivial. I can just take q1 equal to q and all the other polynomials equal to 1. But the interesting part comes now. We can then choose them in such a way that each of the polynomials, the degree of each of these polynomials qi is at most 2. So they are either linear or quadratic for all I between 1, 2, and k. And there's one more statement. If there's a polynomial with, one of the qi which has degree 2, so which is quadratic, then it follows that qi is non-zero for all real numbers. So qi non-zero for all x in R. So we can always find such polynomials and have these interesting results. So this means basically all of these factors are either linear or quadratic with this additional property, and these were basically then the denominators of the rational functions that we've seen so far. And this is kind of the key of how we basically want to, in the general case of p divided by q, we want to decompose q like this and then do some nice computation with this. So first of all, just one more remark on, okay, there are those polynomials, but how do you find them? It's a very standard strategy, so basically which doesn't work always for each polynomial, but it works if the polynomial becomes 0 at some point. And this is usually, I don't want to tell you the whole method or what to do or whatever, but strategy of decomposing such a polynomial. If we have some point a where q of a is 0, if we have some fixed value a that we know, so if this holds for some a in R, then can choose the first of these factors, q1, as x minus a. This is always a factor of a polynomial. This is also actually a theorem that we need to prove, but we don't at this point, but we can always kind of factorize x minus a in this decomposition. And then find another polynomial p1 such that q is x minus a times p1 by the so-called polynomial long division. So this is kind of just some standard computation method. In case you know it, I just write this here, otherwise you don't have to care at this point. But this is kind of how you can make the polynomial smaller and smaller by using their zeros. And then, okay, of course, here we then this factor, then we have to apply the same thing to P1 and so on, and hope to arrive at some point where we can kind of see this factorization. Let me do two polynomials as examples, which I shall study in the integration process later on. Very simple ones. The first one is x to the 4, let me call this, by abuse of notation, I'm calling this p of x. Sorry, this is not related to that p up there. X to the 4 minus 1. Here we can use, this is basically something that you don't have to do this procedure there, because, okay, we would see that 1 is it becomes 0 if we insert x equal to 1, and it becomes 0 if we insert x equal to minus 1. But you can use here the kind of standard theorems. This is what I call this binomial formula earlier in this lecture. Because here you can see that this is kind of a difference of two squares, namely x to the 4 minus 1 is the same as x squared minus 1 times x squared plus 1. And here, this is again a product of two squares, the difference of two squares, so we can apply the same procedure to this again to get that this is x minus 1 times x plus 1 times x squared plus 1, and x squared plus 1 is obviously non-zero for all real numbers, so this is some decomposition we searched for, so we're done with that. Okay, second function, also not too hard, but also with a nice trick. So here we take p of x equal to x to the 3 minus 1. Again, we can here now see that if we insert x equal to 1, we have a 0 here, so x minus 1 should be somewhere included there. So p of 1 equal to 0, and we can now use the geometric sum formula. I hope you still recall it. Namely, if we write x3 minus 1 divided by x minus 1, this is the polynomial we're searching for, just by expanding both numerator and denominator with minus 1. This is 1 minus x to the 3 by 1 minus x squared, and this is now precisely the one side of the geometric sum formula, and this now says that this is the same as 1 plus x squared. And this shows that x to the 3 minus 1 is the same as x minus 1 times this polynomial. I just reorder it by degree, x squared plus x plus 1. And you can see, this is easy to check, that x squared plus x plus 1 is non-zero for all x in R. So indeed we have our decomposition here that we wanted. Okay, so much for that. Now, if we now have this general setting for, again, we write this f of x is p of x divided by q of x, so again some arbitrary rational function. We decompose the denominator, q, explicitly. And by explicitly I mean the following, and this now looks horrible, but this is kind of what you get when you want to compute something, or when we want to have a formula where you can insert numbers. So we can describe q as a product of real functions and quadratic functions which do not become 0. Let's write these functions explicitly, namely, we can show there exists some m and r in n, numbers k1 to km in n, c a1 to am, b1 to br, C1 to CR in R, such that the following holds, such that Q of x, so first of all we can write this as the product of the first linear polynomials, so we would have something like x minus, first of all, sorry, we can pull out some constants. So basically pull out the constant c, and then so that basically you assume then we have a polynomial where the leading coefficient, the coefficient of the highest power, x to the n, is just 1. This is something we can always do, so this is just some constant. And then we can use, assume that all the similar quadratic functions have 1 as the leading coefficient here. So we can write this as the product of linear functions, so this would be x minus an to x minus a1 to x minus an. something like this, but of course, now I haven't assumed anything, but now m, not n. Some number m, which is might be some number here, but of course the same factor can appear multiple times. So I want to sort this and assume that all these I are different numbers, and so I write these as powers, where these k1 to km are my exponents. So this appears k1 times as a factor, this km times, and the between you can figure out. Now for the quadratic functions, we have some more quadratic functions, and these are just given as x squared plus 2b1x plus c1 times, and so on, until x squared plus 2b2x plus, brx plus cr. So we have r different factors here, which are different quadratic polynomials, and we can choose them such that the quadratic polynomials are non-zero for real numbers. So x squared plus 2bix plus ci is non-zero for all x in R. And for all I between 1 and R. Okay, do you want numbers? I'll give you numbers. This is the explicit decomposition, which of course is not as neat as the one which I can just write in here, but we did it, so we have this general decomposition there. Now, this is now the point, yes, I should erase again because I need some space here, and this is not enough. Let me quickly erase and then we go on. Okay, the short version, f is this rational function which is a quotient of p and q has this decomposition form. So we have these linear factors or powers of these linear factors and these quadratic polynomials. And the idea is now that we will use the following result, which is also elementary to prove, although it's a bit of, it's basically the proof is just long because of all the formalism, but it's not very difficult. The so-called partial fraction decomposition. The idea is very simple. If I have two fractions with different denominators and I want to add them, I have to bring everything into the same denominator by expanding the fractions. And there are some situations where we have seen some, for example, really some, I think in the discussion of series we had some, where you can kind of, when you look at something wisely and see that the denominator is a product of certain functions, that we kind of invert the process and write the same as the sum of fractions which have simpler denominators with the different factors. Okay, this is still doable if we have two different factors, but here it's more difficult because here we have a lot of factors. We have these linear polynomials, we have these quadratic polynomials, and not only that, I mean, we can view every power of x minus ai which is in there, so not only the highest power which is included to the power of ki, but also all lower powers can also be seen as individual factors here in this polynomial. So can we kind of decompose this into kind of, fractions with simpler denominators in some way? And the answer is yes. Namely, in this situation with all this notation, the partial fraction decomposition theorem says that there exist numbers, and now it gets messy, lambda ij in R, which is indexed by I between 1 and m, so the number of different linear factors in there, and where j goes from 1 to the power of the ith factor, to ki. Also we have numbers mu1 to mu r, and nu1 to nu r in R, such that, and now we can really use we can decompose the function f of x. F of x is then given, and number c, some constant, this is the c there. F is given by c times, and now we sum up, so we take the first linear factor, so here we have lambda ij divided by x minus, lambda 1j, x minus a1 for all to the power of j, where j is going from 1 to k1. So we're really we really have to include all the powers, so each one gets a different summand here. But there are some real numbers so that this appears as summands, plus and so on, and this is for all the linear factors. So in the last one is the sum from j equal to 1 to km, to lambda mj divided by x minus a m to the power of j. Okay, so much for the linear terms, and these quadratic terms, they appear individually, but here all we can say is that if we just decompose it like this, that in the numerator of the corresponding fraction there is some linear function, because this might not only be a constant but some linear term. Namely, this looks like the following. Oh, I forgot to add the c here and c here. C times, and now we go from I equal to 1 to r, mu ix plus mu I divided by x squared plus 2bix plus ci. Okay, this is a horrible formula, but this is useful because now we can integrate f. If we take a look, let's split this into two parts. So let's first consider this function here, which contains everything associated with the linear factors. This I call f1, and the second part here is f2. And we've seen that these two can be integrated. So first of all, f1 we can integrate, and now to get it even more horrible, I write down the explicit formula. f1, all the functions included in here. Some constants, they are irrelevant for integrating, so they can just put outside. But here we have x minus something to a power. And this is precisely this class of examples that we already had. Namely, this is either if j is equal to 1, we get a logarithm as an antiderivative, or again, some rational function there again. And we can just use this formula. So that was step 2. And this then looks as follows, and this now gets a little messy. The integral from a to b of f1 of x dx is the same as, first of all, we have to kind of separate the part where the logarithms appear. This is the sum from I equal to 1 to m, so let's use all these simultaneously. So the first part, this is j equal to 1. This is where we have to include the logarithms. And so the corresponding summands in the integral become lambda I comma 1 times log of the absolute value of x minus ai, absolute value bracket, plus the rest. So there we have the sum, now it's a double sum from 1 to m, and now we take the summands that start with 2 to km, and this becomes lambda ij divided by, and now 1 minus j, if you just use the formula from above, x minus aj to the power of j minus 1. And this whole thing, this function here in the bounds from a to b. So this is an antiderivative of our harmless function p over q. Of course, now there's a problem because, you might already see the issue. Even if we have the ai, we need to find this lambda ij. So this is quite some work, and there I don't present the general method, but we will see an example of how to do this in a bit. Let me do this integral first, the integral of f2. This one we've considered in step 3. This is precisely the form we had in step 3, so we can just apply this formula. So integrate f2 with step 3 as follows. The integral from a to b f2 of x dx is the sum over all I equal to 1 to r, mu I over 2 log of x squared plus 2bix plus ci. And now in my new notation, this is just the formula applied. Mu I minus bi mu I divided by the square root of ci minus bi squared. I need more space. sorry, second try. Mu I minus bi mu I square root of ci minus bi squared of the arctan of x plus bi divided by the square root of c minus bi squared. So this as a function in x. Okay, here we need brackets, so here we need to sum everything over I. And now this whole thing with a bounds from A to B. And now the general formula for f would be the sum of these two, which I refuse to write down again. But here you can see that this is, this is finally the formula for the integral. But this is now maybe support for the, this is evidence for this claim that I had that integration is art, because this is really tricky. So this is a really long procedure to compute this, and it also really takes a while when you have complicated explicit examples. And really, I mean, who would have guessed that you have arctans and logs in there inside, and there's kind of no way to guess this function right if you start with some harmless rational function. Now, of course, the problem is then to find all these constants, these ai, this bi, mu I, and so on. And so I will give you an example of that, or two examples, namely the two polynomials I had before in the factor decomposition. Now I will compute their integrals. So, example 540. So, f from R without minus 1, 1 to R, f of x is 1 over x to the power of 4 minus 1. By the factor decomposition. So that was example 538. We need to find, so, and then applying this partial fraction decomposition theorem to this, we need to find numbers. Let me just call them A, B, and C in R, such that, and this is now using the factor decomposition, f of x is, so the three factors were just x minus 1, let's start with the other one, x squared plus 1 was the quadratic one, and then we had two linear ones, this is b over x plus 1 minus c over x minus 1. And since every factor only appeared once, there are no powers that we have to consider or something. So this is of this form. So this is 1 over x to the 4 minus 1. And so to find these values, the general method would now be to multiply everything with x to the 4 minus 1. Then we would get here some polynomial and then compare coefficients. This we do in the second example, but here you could use, we can just look at this a bit smarter. Namely, we can see the following. 1 over x to the 4 minus 1. This we had first decomposed in the first step as x squared minus 1 times x squared plus 1. And as it turns out, if you take a close look at these things, this is some standard situation that you often consider. This is the same as 1/2 over x squared minus 1 minus 1/2 x squared plus 1. This is just something, some standard situation that you can do. And then you apply the same thing to this there again. So this is 1 over 2, and now we have the two summands, and the first one can then be decomposed again. Minus 1 over x squared plus 1. And yeah, if you take a close look here, this is the same trick as we used there. Again, we have this decomposition of 1/2 and 1/2, and finally get that this is 1/4 times x minus 1, so let's do like this, minus, so if, yeah, doing the same trick again, minus 1/4 of 1 over 4x plus 1 minus 1 over 2x squared plus 1. So this is the partial fraction decomposition of the function 1 over x to the 4 minus 1. And these are now of the form that we can integrate. So this implies the integral from a to b of 1 over x to the 4 minus 1 dx is 1/4 of the integral from a to b of 1 over x minus 1 dx minus 1/4 of the integral of 1 over x plus 1 dx going from a to b minus 1/2 the integral a b 1 over 1 plus x squared. Let me already write this in a way so we can see what happens. And these are all integrals that we know. This is the same as a quarter log of the absolute value of x minus 1 minus a quarter of log of the absolute value of x plus 1 minus 1/2 arctangent of x, and this now in the boundaries from a to b. And this can be slightly simplified by just using the logarithm laws. This is the same as 1/4 of the logarithm of x minus 1 to the absolute value divided by this, and we put this into one big absolute value. This is just simply by applying logarithm laws. Okay, this evaluated in B and A. Okay, this was relatively simple, but as you could tell from the theorem before, this can be arbitrarily complicated. Okay, let me erase one more time and then we see the next example. Finally, we consider the function 1 over x to the 3 minus 1, and we have already studied the factor decomposition of this polynomial by example 538. This was the product of a quadratic factor and a linear factor, and this means basically for the partial fraction decomposition, we need to find A, B, C in R such that 1 over x to the 3 minus 1 is equal to the following sum of partial fractions. On the one hand, we have the factor x minus 1, so we need some constant over x minus 1, plus, and now the quadratic term, here we have some linear function in the numerator, so bx plus c over, and that was x squared plus x plus 1, such that this holds for all x in R. Okay, now, how do we find these numbers? This is now, of course, non-trivial, and this is now an example of basically the general method that we mostly use if it's not entirely obvious how to find these numbers. Namely, we take the whole equation and multiply everything with x to the 3 minus 1. Then we know, since here are some of the factors, the other factors are just remaining. So this basically means that here we have 1, r without 1, sorry. So this becomes 1. This here, there's one factor out of there and the other factor remains, which means this becomes a times x squared plus x plus 1. And here we have this factor gone, so this is bx plus c times x minus 1. Okay, this is a quadratic polynomial, and we just rewrite this by taking quadratic terms and linear terms and so on separately. This is then, let me just take a peek here, a plus, so equivalent to 1 is a plus b times x squared plus a minus b plus c times x plus a minus c, and this needs to hold for all x in R without 1. But as you can easily see, I mean, this is some quadratic polynomial, and this is also a quadratic polynomial in the sense that the first two coefficients are vanishing. So this can only hold by some theorem of polynomials that technically we haven't proven in this lecture, but that basically two polynomials coincide if and only if their coefficients coincide. I think we haven't seen this there. So this is the case if and only if this here is 0, a plus b is 0, and this has to be 0 as well. And this constant term here has to be 1. A minus c is equal to 1. Okay, this is now what's called a system of linear equations, and you will see next semester there's a general method of how to solve this. I mean, this is something that I guess every one of you could by just elementary, combinatorics or arithmetics here. It's not too hard actually. But what I want to I want to give you the results so we can find. So there's a unique solution. One solves this, so the general procedure is done in the next semester in Mathematics 2, in linear algebra, as the following. A is equal to 1/3, B is equal to minus 1/3, and C is minus 2/3. So if we insert this in this formula, we get 1 over x to the 3 minus 1 is the same as 1 over 3 times x minus 1. And now minus x plus 2 divided by 3 x squared plus x plus 1. Okay, this we can now integrate. The integral from a to b 1 over x to the 3 minus 1 dx is now the same if we pull out the constant already. 1/3 of the integral of 1 over x minus 1 dx minus 1/3 of the integral from a to b of x plus 2 divided by x squared plus x plus 1 dx. Okay, this is, the first one is easy. This is again 1/3 log of x minus 1 to the absolute value in the boundaries from a to b, and this integral we do separately, so just the same here. So this is precisely of the form we had before. Linear polynomial divided by a quadratic polynomial. And there basically we just need to include the above formula, use the above formula with the coefficients in here. And so I'll just give you the result by the above formula. The integral of x plus 2 divided by x squared plus x plus 1. So in the notation of before, mu would be 1, mu would be 2, r would be 1/2, and s would be 1. And if we just insert this, first the logarithm part, there we just had mu over 2, so 1/2 of the log of the denominator, so x squared plus x plus 1. And then we had the arctan part. This is then nu minus r mu was the case, so this is 2 minus 1/2 in this situation, and the square root of this minus that 1 squared here, as this is 2 twice 1/2, so here we get 1 minus 1/2 squared, which is 1/4, of the arctan of x plus 1/2 of square root of 1 minus 1/4. So in the boundaries from a to b, and of course this can be slightly simplified. If we just compute a bit, this is 1/2 log x squared plus x plus 1. And this here, this expression here, this is square root of 3/4, so this is actually square root of 3 over 2. And playing around with the equation, we get that this is the same as plus square root of 3 times the arctan. And here we just need to expand the fraction. Basically, this is 2x plus 1 divided by the square root of 3. And this in the boundaries from a to b. A to b. And now finally we have to include this in this formula. So finally what we get is integral from a to b 1 over x to the power of 3 minus 1 dx, which is a harmless looking function, and its integral is 1/3 log of x minus 1 to the absolute value minus, and now we have 1/3 times 1/2, so 1/6 log of x squared plus x plus 1. And here we get, so square root of 3 divided, minus. Square root of 3 divided by 3 is 1 over the square root of 3. Arctan 2x plus 1 divided by the square root of 3. And this now from a to b again. So this is the result. And the only thing we could slightly simplify is summarize as logarithms, but I don't know if this really makes things better. So this could be the same as 1/3 log of, and it's now playing around with the logarithm laws. Here we get 1/6 is a third times a half, and if we put the 1/2 inside the logarithm, we get this, minus 1 over the square root of 3 arctan, of this, and this in the boundaries from a to b. Phew, this was work. This was quite some work. But here you can really see that some function that would be easy to differentiate is quite hard to integrate, and you get some result which is highly non-obvious. I mean, no one would have guessed from this formula that this is the result. Okay, I hope I convinced you that really integration is art. And there are many, many, many more interesting integral tricks, and especially from this integration of rational functions, you can reduce many other different cases to integrals of rational functions. So you first need to do a complicated computation, then you can apply this machinery, and basically it's it's possible to let you compute integrals which are arbitrarily long to compute. And of course, many computer algebra systems have methods to solve integrals. For example, Wolfram Alpha is very smart with this. But I think it's really good to see these tricks because to really understand how this works. I mean, just throwing some numbers into a program and getting another number out of it, this cannot be everything if you really want to understand things. Okay, this ends chapter 5, and this also ends the first calculus part of your mathematics lecture series. At this point, we basically hit the hard break and go a few steps back. Namely, we have now discussed everything in one variable in the sense that functions were just defined on intervals or on subsets of R. And the next calculus aim would be to have a calculus for functions which are defined on R to the n, so functions in several variables. And to define derivatives of such functions and convergence and continuity notions and so on for these things as well, because these are really natural objects appearing everywhere in science. So what we first need to do is to do some linear algebra, because we need to kind of understand R to the n a bit better and to see how this works. There will be a generalization of notion of linear, so we have linear maps we will see, and we will see a general notion of vector spaces, which are also very naturally appearing in all parts of physics, and also even in infinite dimensional vector spaces appearing in quantum mechanics right from the start. But you should see this later, but this is kind of at the point where we first, we stop with calculus, start again with linear algebra, and for your consolement, basically the next chapter will be, again, the proofs and so on will be much simpler than this. So we kind of go a bit back to the start simple again, and then work our way through to linear algebra before we return to do calculus. So, see you in the next chapter.